Welcome back. Our previous video went over some of the main machine learning algorithms that are used quite frequently. And in this video, I wanted to go back to the idea of balancing bias and variance and talk about how we actually implement that process to make sure that we're not overfitting with our prediction model. And for this, we need to understand two fundamental ideas. One is called regularization, and the other is called cross-validation. And these are essential parts of the machine learning workflow. And we also need to master these concepts if we want to be able to utilize machine learning for econometric analysis. So the main question is, how do we ensure that our model is not overly complex, meaning that it's not overfit? And the answer is to penalize complexity. And the way that we do that is through a process called regularization. And then cross-validation is the way that we prove that we've got the optimal level of regularization. Now let's talk about how cross-validation works. And for this, I'm borrowing from the notes of Ryan P. Adams, who is a computer science professor at Princeton. And I'll post a link to his whole notes in the description if you're interested. But basically, we have our data set, and the blue and the red is our data set. And we're going to chop off some set of the data to serve as the test set, and we're going to put it in a safe and only use it to evaluate the model at the very end. And then the remaining chunks of data, we're going to have take turns serving as part of the training set or part of the validation set. So we have these different folds. These are just different ways we can split this remaining data into validation or training. And we've taken 4 chunks of this training data, and we're just going to have a different chunk take its turn in the validation data. Otherwise, it's going to be in the training data. So this would be called 4-fold cross-validation. And what we do is we estimate the parameters of the model, or we train the model using only the blue data set. And then for a given parameterization in the blue data set, we're going to go into the green data and see how well our trained model performs. And the green is meant to serve as a lens or a preview of what's going to happen in the actual test data. So we want to use the green data to assess performance and the blue data to train the model. And we can try different values of complexity, and the way that we impose that complexity, it depends on the algorithm we're using. I'll talk about that in just a moment. But we might have some hyperparameters that are going to govern the complexity of the model. And so we can repeat this 4-fold process for all the different values of this hyperparameter that's going to govern a wide range of model complexity. And then from there, we can see, well, which one was the best performance in this validation set? That's what I'm going to choose for my optimal complexity. And then that's what I'm going to take into the test set when it's go time. So you might be wondering, why don't we just have one green data set? Why don't we just use fold 1? And we can do that. We call that a holdout sample as opposed to a cross-validation fold. But the idea of doing the folds is to get a better sense of what the average prediction error is going to be in the test set. We don't want our prediction or our hyperparameter values to be tied to some randomness in this way that the data was split. And so doing this multiple times helps us average out over that randomness. And then you might also be wondering, well, why not stop at 4? Why not go to 10 or 20? And in truth, we can do something called leave one out cross-validation, where we have just a single observation in the validation, and then we have each observation take turns being in the validation set. And so we'd have n minus 1 folds. But that's not actually going to be useful because at some point we've sort of got too much noise in that validation set. So we want to kind of keep things reasonable, both with regards to computationally, because we have to repeat all of our training in each fold, but also we need to have enough variation in the validation data to give us a meaningful goodness of fit metric. And so typically rule of thumb is to do something between 3 and 10-fold cross-validation. So then how do we actually get these hyperparameter values that I just talked about for regularization? Well, it's going to depend on the algorithm. In tree models, we would think of the complexity as the number of leaves on the tree or the number of branches that the tree can have. In linear models, the complexity could just be the number of covariates that are in the model. In neural networks, there's complexity in terms of the network architecture, which has to do with the number of hidden layers and the number of neurons per layer. In a Bayesian approach, the prior belief is going to act as a regularization, and so typically Bayesian approaches don't need regularization. But whatever our algorithm, there's always going to be some sort of hyperparameter that we can tune using this cross-validation process. And if our algorithm is linear in parameters, then we can use some special types of regularization that I'll talk about now. One is called L0 regularization, which is also known as subset selection. There's also L1 regularization, which is called LASSO, which stands for least absolute selection and shrinkage operator. And then there's L2 regularization, which is called ridge regression. And so let's talk a little bit more about these, because these are going to come up quite a bit when we try to take machine learning into econometrics. And the reason for that is that a lot of econometrics is linear in parameters. So L0 regularization is basically just going to say, okay, I have L possible X's in my model, and I'm just going to choose which X's to include in the model and which ones not to. So this is some automated version of what we typically do in econometrics. We typically just say, okay, these are the covariates in my data set. I'm going to just include some subset of them on, in my final regression model, and these are the results. If we were doing L0 regularization, we would probably be using either the adjusted R squared or some penalized version of the sum of the squared residuals to penalize the complexity. And there's two ways that we can do this algorithm. We can start with an empty set of covariates and build up the set that are included. Or we can start from the full set of covariates and pare it down until we get to the right amount. So these are called forward and backward stepwise regression. And then the main weakness of this L0 regularization is it only works if we have fewer covariates than rows of our data. But in a lot of applications, so-called high-dimensional applications, there's actually more covariates than there are rows of data. And this violates the OLS rank and order conditions, and so we need something different for this case. And that's where we get to lasso and ridge. With lasso, we're going to take let's just take the usual OLS objective function, which is to minimize the sum of the squared deviations. And then we're going to add a penalty term that's lambda times the sum of the magnitudes of the betas, where magnitude here is the absolute value. So we're going to set some betas to be 0, and others we're going to attenuate towards 0. And then another option would be ridge regression, where we have the same penalty term, except instead of using the absolute value, we're going to square the value of the beta k. And so in this one, we're going to have betas that are just attenuated in magnitude. They're not going to ever get to 0. And the reason for that is because the absolute value function, if you just graphed f of x against x, where f of x is the absolute value of x, it's going to look like a V, and the vertex is going to be at the origin. So that's non-differentiable at the origin. Whereas if you just graphed a parabola where f of x is x squared, that's going to go through the origin smoothly. And so that's why the lasso is going to end up shrinking some of those all the way to 0, but the ridge is not going to. Regardless of what specific penalty term we're looking at, we have a hyperparameter lambda that can govern how complex the model is. If lambda is close to 0, we're basically having no penalty for complexity. Whereas if lambda is really large, then we're going to have a really strong penalty on complexity. And so the value of lambda is going to govern how much complexity we're going to allow, and that's the process of regularization. So we want to choose the optimal lambda that satisfies the bias variance trade-off that we talked about a couple of videos ago. And we're going to do this by using the k-fold cross-validation that I illustrated earlier. If we wanted to, we could also employ a weighted average of L1 and L2 regularization, which is called elastic net, but that's not necessary. But if we did want to use elastic net, then we could have separate penalty parameters on the lasso and the ridge portion. And the nice thing about L1 and L2 is we can apply this to anything that's linear in parameters. So it doesn't have to be just an OLS or a logit. It could be a neural network. It could be a support vector machine, and a lot of other options. But the key thing is that L1 and L2 work well even if we have more covariates than rows of data, which happens a lot in many different applications. And just to remind you, high dimensional means that the number of columns in my X matrix exceeds the number of rows in my X matrix. Now you've officially got enough of a basic understanding of machine learning to appreciate how we can augment econometric analysis with machine learning to get the best of both worlds. And that's what the next set of videos is going to be in this series. So I hope that you'll find it interesting to see all the different ways that econometrics is incorporating these tools from machine learning to improve the quality of the analysis. So I hope to see you in the next set of videos, and thanks for joining this one.